Welcome to the exercises for Chapter 7. The first couple of exercises are focused on covariance and correlation matrices. So, in this chapter, in the text, I explained the relationship between covariance and correlation. In particular, they are almost exactly the same. The correlation just has a scaling factor. In particular, we scale by the product of the norms of the two variables, assuming that the variables are mean-centered. So what we are going to do in this exercise is implement that matrix-wise. Instead of transforming a covariance to a correlation one pair of variables at a time, we're going to do it for the entire covariance matrix. Here's the formula. So C is the covariance matrix, R is the correlation matrix, and S is a diagonal matrix where the diagonal elements, so all the off diagonals are zeros, of course, and the diagonal elements are the reciprocals or the inverses of the standard deviations for each variable. So notice that we are pre and post multiplying by a diagonal matrix. That is because of the special properties of multiplying by diagonal matrices, and that I introduced you to, and we had some discussion about that in Chapter 5, Exercise 11. So you might want to go back and check out that exercise if you feel like you would benefit from a refresher of this discussion about why we pre and post multiply by the same diagonal matrix. Okay, so yeah, so that's basically all we want to do in this exercise is transform the covariance matrix into the correlation matrix. This is using the data set that we have been working with earlier in this chapter. And then, yeah, I think we can also create a visualization where we see the data covariance matrix and transformed into a correlation matrix here. If you are just coming to this code without already having gone through the code from earlier in the chapter, then if you try to run my solution code, you're going to get an error. Okay, so I didn't get an error here. You will get an error if you don't run the previous code, and that's because this variable here, covmat, is created earlier in the code. Let me see where that is. That was in the beginning. So that was where we imported these data from this machine learning database. It was the data about crime statistics in different communities. So anyway, if you get an error message then about not having the data imported, then you just need to come back up here to the top of the code. Run, let's see, you would run this piece of code and this. Here you can see it's the data matrix, and here we are creating the data covariance matrix. Okay, so now we have that covariance matrix, and now we can go down and continue on exercise 1. Okay, so here is the main piece of code. This is a pretty straightforward translation of the linear algebra equation that I showed into Python code. And yeah, you can see we're just pre and post multiplying by this diagonal matrix S. And it's a diagonal matrix where the diagonal elements are 1 divided by the standard deviations. And I get the standard deviations from the variances, which themselves are the diagonals of the covariance matrix. So the diagonal elements of a covariance matrix are the variances of each variable. To get standard deviation, we take the square root of that, and then this matrix S is 1 divided by those standard deviations. Okay, so then we can see the covariance matrix, which we already saw above, and the correlation matrix, which comes from the covariance matrix. It's just been transformed through a normalization, which guarantees that the smallest or most negative possible correlation is -1, and the most strongest positive correlation is +1. So how do we interpret this correlation matrix? So we can see that the correlation between variable 20 and 80 is positive, and that correlation is, fairly robust, maybe somewhere around 0.5. Now, to know what that means, to be able to interpret that, you would need to go back and find which variables correspond to, the 20th variable in the data set and the 80th variable in the data set. And then you could see what those two variables are. You could plot one by the other and see how they are related to each other. You can see that these correlations do not look random. It looks like there's some structure in there. There's a lot of variables that are meaningfully positively correlated and other pairs of variables that are negatively correlated. So there is structure in this matrix. There are patterns in this matrix. We can use an analysis method like principal components analysis, for example, to help us understand and identify these patterns, these latent structures in the data. Those are the kinds of analyses that I will cover in later chapters in the book. Here, I've just written some additional code. This is not part of the exercise. I just thought it would be nice to have. So basically here, you just specify a row and column index, and it's going to print out the correlation and then the actual data values for those two columns. So we can see that the correlation of percent divorce for males and median income is minus 0.76. So that's a pretty robust negative correlation. And the interpretation is that people or communities with larger median incomes have lower rates of male divorces. So this would be a good way to start exploring a data set and use principles of linear algebra like dot product and covariance and correlation norms, vector norms, to help you understand the meaningful patterns in a data set.